Another important factor we have to talk about here is about the batch size for optimization. So for the previous page, we only consider the gradient descent, this algorithm in scenario. When we apply the gradient descent to the real-world application problems, we have to consider the data size, right? So the data size will affect the way we define the loss function for optimizing the model, right? Or for calculating the gradient. So depending on the size of the data we use for defining the loss function, before we mentioned that we have to define the loss function, right? But we didn't mention how do we define the loss function, what kind of data we can use for defining the loss function, right? And in this page, we show you with a straight way for defining the loss function with different amounts of data for our model. The first way we define loss function is with a for batch. And let's assume we have a training data as shown here. And we can define a loss function with all the data instances in our training data set. And we use them all together to define a loss function. In other words, we use the for batch for defining a loss function, right? And if we enumerate all the training data in our training data set and sum them together to define the overall loss function for this variable, right? This is L denoting this loss function for one single instance like xi compared with ground truth yi, right? And we sum all the data instances together, then we can define the whole batch or the for batch loss function. This is one way we can define the loss function. If we define them in this way, then this loss function will denoting the overall training data set loss function, right? If we further calculate the gradient of this loss function regarding to the variables, then the gradient will be much more precise and much more correct because we are optimizing with regarding to the overall training set. And this one is also defined based on the overall training set, right? However, this may require more memory because we have to fit or we have to load all the data set into the memory for defining calculating the loss function, right? And also further calculating the gradient. We have to load all the data set into the memory depending on the memory you have as well as data set size we have, right? In most of cases, this data set can be so large. In other words, this way probably cannot work for some larger scale data sets. In turn, we have to rely on some small ways to define loss function instead. Then we can introduce SGD and mini batch SGD instead. This SGD denoting the stochastic gradient descent. For the SGD, we define loss function in another way. So we are partitioning this training set into several batches. And inside each batch, we only have one single instance. In other words, when we are updating these variables, we are defining a loss function based on each of the instances. You can follow me, right? So we are defining the loss function with each of the instances in the training set for the SGD. For example, if we have multiple instances, we can use this instance first for defining the loss function for updating the risk variable, and then we can move forward, use the second instance for defining loss function, and then updating the variable according to the gradient descent algorithm we showed before. You can see, this will only require we to load one single instance into the memory. It will be much more efficient in terms of the memory consumption. Because here we are doing the gradient descent based on one single data instance, right? And this loss function, all the gradient we calculate based on this loss function may not be precise for the whole training set. Because we are doing the optimization with regarding to the whole data set, right? To achieve the minimum for the whole data set. However, the way we calculate the loss function and the gradient will be based on one single instance for one time, right? Its direction may be not correct anymore, for the gradient. So, we have another way which is more like a balance between the for batch and SGD. For the mini batch SGD, right? And in the mini batch SGD, we still partition the training set into multiple batches. However, inside each batch, we will have multiple data instances. And we can decide the size of each batch or each mini batch to be K. And we can represent each of the mini batch to be a B set, which is a subset of the whole training set, right? And then based on these batches, we can define a loss function. So in this way, we just need to load one single mini batch into the memory for defining a loss function as well as calculating the gradient in the following steps, right? It will not consume so much memory space, and also it will be much more stable than just one single instance, right? And we can sum the loss values for all the instances in the mini batches and to define the overall loss function and further define the gradient values. So these are the three ways we can define the loss function for the gradient descent algorithm. Depending on the size of the batches we are using, we can categorize them into full batch GD, or the stochastic gradient descent, or the mini batch SGD instead. As to which one to be used for your future projects, it depends on the memory space of your computer as well as the size of the data, right? So if your memory is not large enough to hold the whole data set into the memory, if so, then we can turn to the mini batch SGD instead, which will be much more stable than the SGD. Also, will consume less space than the full batch, right? However, if your data set is not large enough or you have enough memory space, then you can try to use the full batch SGD instead. It will be much more stable than SGD as well as the minimum batch SGD. Okay, you may wonder what will be the performance for these different GD algorithms like full batch GD, SGD, and mini batch SGD. On the right hand side, we show the performance analysis of these different methods in the learning process. Because remember, when we are doing the optimization, we are learning the optimal values for the whole data set, right? If we use the full batch GD, the target will be the same as our optimization target, because we are also doing the gradient descent based on the whole data set, right? Its advantage is more robust, also fast to converge. If we're doing the full batch GD, the gradient we calculate at each point will be the same, or will be pointing directly to the minimum of this loss function, right? So it will be converging very fast in terms of the steps, because we will go straight forward to the minimum of the loss function. And the advantage with the full batch GD will be robust and also fast to converge in terms of the gradient direction to the minimum, right? However, it also has some disadvantages. It will require far more memory space, also will be slower in computation, because in each step we have to calculate the gradient of the whole data set towards this variable, right? Each step will consume more time. However, we will have fewer steps to achieve the convergence for the full batch GD. As to the SGD, because we are defining loss function with one single instance in the training set, right? So if we are calculating the gradient at some point with one single data instances, its gradient may be not necessarily the same as the gradient for a whole training set towards the minimum, right? In other words, its direction will be divergent. We may go to some other locations, maybe based on this single instance, because each instance will be so random, right? Its gradient will be so random. In other words, its learning process will be more like zigzagging, right? We have to move zigzag until we can achieve convergence to the local minimum, right? So for this SGD, its advantage will be, it will be fast in computation. In other words, in each step, we just compute the gradient for one single instance as well for the loss function, right? And we can use a very small memory to hold the single instance in calculation. And it also has some disadvantages. It's not very robust because we have to move forward according to the misleading gradient for the single instances, and we have to move in a zigzag way until we can achieve the convergence. It's not robust. Also, gradient can be slightly misleading compared with the straightforward gradient towards the minimum by the full batch GD, right? So it can slow down the convergence process. As to the mini batch SGD, it will be more like a balance between them, right? Compared with the full batch GD, the learning process will still involving some misleading steps because we are computing the gradient based on mini batch. It's not the whole batch, right? Its gradient maybe is not the same as the gradient for the whole data set towards the minimum. In other words, we also have to move slightly in a zigzag way until we can achieve the convergence. And compared with SGD, however, will be much more robust, right? Because we rely on the mini batch instead of the one single instance. Also, it will consume some memory space, but not large enough, right? So this mini batch SGD will be normally used in the optimization if the data set is larger than your memory space. I'd like to recommend you try the mini batch SGD in your project, and you can also compare different batch sizes in your project as well to see their performance in updating as well in the learning process. Okay, so this is a gradient descent algorithm as well as some important issues we have to discuss in the lecture.